As your study of the electronic structure of atoms continues, understandably, it can be kind of overwhelming and confusing when you first start. It's helpful to understand that we've looked at the electronic structure of atoms in at least two different models in times past. In more modern times, we have designated one model to be the most correct model, but in times past, as I said, we can look at the electronic structure in a couple of different ways. Originally, the Bohr model of the hydrogen atom saw the electronic structure as an electron orbiting the nucleus, much in the same way a planet orbits the sun. But as we increase our understanding of the electronic structure and how that world works, many things just did not fit with that model. The more current model, called the quantum mechanic model of the electronic structure of the atom, tells us that we cannot know the exact place or speed of the electron at the same time. We can't really know exactly where it is at any given time. Therefore, the electron travels in an orbital around the nucleus in random fashion. This is helpful to understand the electronic structure of the atom as we go on. To help us visualize this a little bit more, we'll use 4 quantum numbers to discuss and to explain this model. The first quantum number we will designate as n, and n can be any positive integer, 1, 2, 3, and so on and so forth. N stands for any main energy level of that electron or the shell. So in our quantum mechanic version of the atom, we have an orbital shell in which the electron could be traveling anywhere within that three-dimensional space at any given time. And as the energy level increases, so does the distance from the nucleus, and therefore the energy of the atom. So when we talk about the energy level of the atom, we might designate this shell as n equals 1. And if n equals 1, we'll say that its orbital distance is about like such. Now, if n equals 2, this means that the value of n is a higher energy level, a higher shell number. That means that the energy of the electron is greater and also the distance. So if n equals 2, that means it might be something more like this in distance-wise. Now, our next quantum number we will designate as L. And L is going to represent the shape of the orbital. We also will refer to this as a subshell. L is dependent upon n. L can be any number starting with 0, 1, 2, up and into n minus 1. So if we think of L being dependent upon n, any number up to n minus 1, let's say n equals 1. This would mean if L is n minus 1, L would be 0. Now, when L is 0, our orbital is a s orbital, and all s orbitals are spherical. Remember, this is a three-dimensional sphere. That is very important to remember. Now, if n equals 2 and L being n minus 1, that means that L has to be 1. Whenever L is 1, this represents a p orbital. And p orbitals are going to be much in this shape. You can refer to it as a bow tie. You can refer to it as dumbbell shaped. Whatever helps you remember it easiest. Our next quantum number we will refer to as m sub L. M sub L represents our orientation around the nucleus. So this is going to be our orbital and how it orients itself around the nucleus. Now, what's really important to remember here is that m sub L is dependent upon L itself. And m sub L is designated as any subshell that's negative L to positive L. If that's confusing, that's okay. So let's try one out. If L is 0, we said earlier that this represents a s orbital. And s orbitals are spherical. Now, we said that m sub L represents negative L to positive L. So this means that m sub L will also be 0. Because our s orbital is spherical, if you think three-dimensionally of our nucleus on a three-dimensional plane, a x, y, and z axis, our orientation can only be one way. Let's try another one. If L equals 1, this means that m sub L has to be everything between negative L and positive L. Therefore, m sub L will be negative 1, 0, and positive 1. So that means we have three distinct orientations that those orbitals can be around the nucleus. In order to envision this, we have to remember that if L equals 1, we are talking about p orbitals, or our dumbbell-shaped orbitals. And we have three different ways we can orient these. Well, if we have a three-dimensional plane, much as we had earlier, a z and y axis, we can first try it around the x-axis. And we know that that electron is traveling somewhere within that three-dimensional p orbital space. Now, we also have m sub L equals 0. So this means that our electron could also be traveling in the z-axis. M sub L also equals 1. Therefore, we could also have it in the last axis. Take some time to review, make notes, and make pictures. Later on, we'll do an experiment in which we'll use balloons around a central figure to help you visualize and see how and why the electrons act this way. You will recall that electrons travel in electron clouds surrounding and at great distance to the nucleus. Electrons like to be spread out, but what we'll also get to later is that electrons do not like to be close to each other. And when you have multiple orbitals surrounding one nucleus, these orbitals and their orientations will spread out as much as possible. But we have one more quantum number to go over. Our last quantum number we're going to refer to as the spin quantum number, or m sub s. Now, although we call this the spin quantum number, you do need to have an understanding that we're not actually saying that the electron is spinning in reality. However, we do designate it in the fashion that you have an electron with two variable spins. We could designate it by spinning kind of like on a top like this, spinning this way or this way. But this isn't actually what's happening in reality. Why we do this is going to be for later discussion. But we use these diagrams in order to demonstrate that we have two possible m sub s values. And we say that those are either m sub s equals positive 1/2, which we designate as spin up with an upward arrow. This will come into play later when you draw orbital diagrams. Or we can say m sub s is negative 1/2 with spin down. This concludes our quantum numbers, and these will help you with our future discussions and with your understanding of quantum mechanics and the way that the electronic structure of an atom works.